In this video, we're going to talk about transition metal organometallic reactions. Now, the problem with these reactions is that, well, spoiler alert, they're kind of weird. When I was an undergraduate, in fact, no one basically had any idea what was going on. These days, people have some idea what's going on, but still, there's lots of mysteries. Now, way back in 1972, when I was a graduate student at Northwestern, a very important paper came out which was submitted by a guy named Chad Tolman, who was at the DuPont company. And what he did was, for the first time, he really took organometallic reactions and classified them into fundamental reaction types. Now, the book uses his reaction types, but not all of them. He published 5 particular reactions. Only 5, doesn't sound like many, but each of them worked backwards as well as forwards, so there are actually 10 when you added the 2 directions together. Now, we're going to go through each of these one at a time, and what we're going to find is that each reaction has the potential to change 3 things about the metal. The metal's oxidation state, the total number of electrons around the metal. By that I mean how many valence electrons are there. Are there 16, 18, whatever, what's the number? And the coordination of the metal, number of the metal. Is it 4 coordinate, 5 coordinate, 6 coordinate? So let's look at these one at a time. We're going to be 5 slides. We'll go through each reaction type forward and backwards and look at the results. So the first one's pretty trivial. It's just a ligand coming on and off. So here we have a palladium complex. It's palladium 0. Palladium 0 is 10 electrons. There's 4 ligands, so it's an 18 electron complex. It's pretty crowded, so a ligand simply pop off, or the reverse, it could go back on. This is ligand dissociation. Or if you look at the reverse reaction, it's Lewisbased association. We call them Lewisbased because the ligands are donating a pair of electrons. Now, when you look at the total classification, the metal coordination number obviously changes, in this case from 4 to 3 and 3 to 4. The electron count changes because the phosphine donates 2 electrons, so you go from 18 to 16 electrons. But the oxidation state of the metal doesn't change. So this is the simplest example. The next example is very, very similar, but not in the book. Why not in the book? Because it's pretty weird and also not very common. A few ligands actually are considered Lewis acids, and one of these is the proton. If you take this anion right here, it's a cobalt in the minus oxidation state. It turns out it's a good base, and it will react with a proton to give a hydride. Actually, it's not that good a base because this is a strong acid. This guy will dissociate if you put it into solution. And so this is not a Lewis-based dissociation, it's a Lewis acid dissociation. Proton comes off. Now this is a little weird over here because we call it a hydride. So one that's on the metal because the hydrogen is more electronegative than the cobalt. We assign the electrons to the hydrogen. So this is a cobalt hydride, formerly cobalt plus 1, but it comes off as a proton. That's pretty bizarre. But it has more to do with the formalities of electron counting than anything very sophisticated. Of course, what's the reverse reaction? The reverse reaction is Lewis acid association. So the reverse, when you put the proton on, you'd be associating the Lewis acid. Let's look at the overall changes. No change in electron count because the Lewis acid doesn't bring any electrons. The oxidation state of the metal changes because of the way we assign the charges in the compound, and of course the coordination number is going to change. Okay, this one's a little bit different. Oxidative addition. We've seen kind of a variation of this before. You take magnesium metal, which has no electrons or has 2 electrons in its valence shell. We add phenylbromide to make a Grignard reagent. The metal gets oxidized, and of course now it essentially has 4 electrons because the bromide donates 2 and the phenyl donates 2 electrons. This is oxidative addition. Well, oxidative addition works in transition metals very much as well, and in fact it's much more common for transition metals. Here we have a palladium compound, 14 electrons, palladium 0, 2 ligands. We add phenylbromide to it, very similar to forming the Grignard reagent. We get a palladium bromide, a palladium with phenyl. Palladium has been oxidized to palladium 2. Total electron count has gone up by 2 electrons. Now you can add a lot of things to a palladium. You can add hydrogen, H2, gas, form 2 hydrides, that's oxidative addition. You could add bromine Br2, and to get 2 bromides, oxidative addition. Quite a few different variations. It's a very important reaction. It's going to show up all kinds of places. Now, oxidative addition, what's the reverse? Well, reductive elimination. So if we up here, if we just pop this off, the phenyl, and got the phenyl bromide back, we would be reducing the metal and eliminating the phenyl bromide. Now over here, this one never reverses itself, so it's kind of silly to draw this one as an equilibrium, but I did it just to be consistent. So you don't see Grignard reagents falling apart to form phenyl bromide, but if you did, it would be a reduction of the metal. So what's the overall summary? There's a change in the metal coordination number. It's going up by 2. The electron count is going up by 2. And of course the oxidation state of the metal is changing. So everything changes with oxidative addition. The next reaction, ligand insertion. Now this is one which really needs a better name. People call this ligand insertion, but what it really is that ligands can migrate from the metal to another ligand. So here we have a methyl on a manganese, and the methyl can migrate to one of the carbonyls and form an acyl compound. This is called ligand insertion because you can think of this as taking the CO and inserting it into the manganese methyl bond. A better name, though, would be ligand migration, where the methyl migrates from the manganese to the carbon. So this is forming an acyl compound from an alkyl compound. Here's another very important example over here. We have an alkene next to a phenyl on a palladium. What can happen is that formally the alkene can insert itself into the palladium phenyl bond, but again, a better way to think about this is we can have a migration where the phenyl goes from the metal to the ligand to form this now alkyl compound. So this is ligand insertion, ligand migration. The reverse reaction would be deinserting the ligand, or a better way of thinking of it is saying the migration goes the other way. If we want to do the reverse reaction here, the methyl would move from the acyl compound over to the manganese. In this example over here, the phenyl would move from the alkyl group over here to the palladium, reforming the alkene. Now, what's the summary here? Change in coordination number and electron count. Oxidation state actually doesn't change because here we have an alkyl compound, here we have an acyl compound. Same oxidation state, but the electron count is different. Same way over here. We're not changing the oxidation state. Both of these are palladium 2, but we're changing the electron count. Okay, next one. This one is not in the book, but the book uses it. And it's an important one as well. It's when you have 2 neutral ligands and you're going to form a bond between the ligands, which ends up oxidizing the metal. So here I have 2 alkenes coordinated to an iron 0. They can undergo a reaction. This is kind of like a Diels-Alder or something in terms of a concerted movement of electrons involving pi bonds. And so they can couple and they can form this 5-membered ring. Now, when you've done this, you've formally gone from iron 0 to iron 2. So it's an oxidative coupling. The metal is going to be oxidized. The example that the book uses is this one over here, where you have this very unusual carbene ligand. A CH2 on a ruthenium with a double bond is called a carbene. It can couple in an oxidative coupling to an alkene and form a 4-membered ring. This is going to be the basis of what we call olefin metathesis, which we'll talk about in class. The reverse reaction, oxidative coupling, is, well, reductive decoupling. Sorry, that's the reverse. And it's simply going backwards. And indeed, in olefin metathesis, the reaction goes forward in this direction, then it turns around and goes back, but we split the alkene carbene this way instead of that way, and we get a different compound than where we started. The summary is change in electron count, 18 to 16, change in oxidation state, it's an oxidation, no change in the coordination number because we consider this 2 coordination, this 2 coordination. So that sums up the fundamental reaction types. And what we'll see is essentially every organometallic reaction that we do can be classified as one of these reactions or another.